quantitatively discuss a solution, we need to use molarity. Molarity is simply the moles of solute divided by the liters of solution, or moles over liters. There are other units of concentration out there, but molarity is by far the most commonly used, and it's the one that's tested. There's a couple other ones like molality, which is not on the AP test, so we won't cover it. You may also see millimolar, which is simply just 1,000th of a molar. So what do you call a tooth in a glass of water? A 1 molar solution. You'll notice that there are 3 terms in the molarity equation. Very commonly, you'll get 2 terms in a question, and you'll have to find out the 3rd term. Here's a mathematical example. If we were to calculate the molarity given a mass and a volume, we will first need to convert the mass into some moles. By dividing by the molar mass, I can now find the moles of sodium sulfate, and now I can simply just divide by the volume to find the molarity. It helps to see whenever you see the capital letter M, remember it's important to use a capital letter, that it means moles over liters. So you have 2 terms given to you with 1 number. That's very helpful. So if we keep some of the stuff the same, and we keep the solute the same, and we're going to still have 2 terms, and we're going to look for a 3rd one. But this time the problem gives you volume and it gives you molarity. So now I'm going to need to find the mass of it. So this is a problem I run into a lot when I'm making my solutions for y'all, because I know the molarity I want to get to and I know the volume of the flask that I have. So I need to understand how much of my solute I need to add to make the proper molarity. When I do this, I will start with my volume, and remember that I put it into liters here. The problem gave me milliliters, but since molarity is moles over liters, for the units to work right, I needed to convert it. And it's acceptable. I will allow AP students to go ahead and just do this step right away in your head. You guys can move the decimal place 3 places to the left, no problem. And when I use the molarity to help me, and this will actually cancel out the liters and get rid of it. That's very helpful, and that will be helpful in later videos and later on in the course. Then I will just multiply by my molar mass to find my mass of solute that I would need to add to the flask. So here's the situation in which a solution is already prepared, and now we're trying to get it less concentrated. We're trying to dilute it. If I started with a 1 molar solution of potassium nitrate and now I'm trying to get to a 0.25 molar solution, I am diluting it down. I'm taking it from a higher concentration to a lower concentration. And turns out that this one just goes by force. You could go by whatever, go down to whatever you would like. And I set up a table for you over here that's pretty helpful. If you start taking down known information, you take the molarity and the volume on the left, and you write a 1 and a 2 on top, and then you start filling in blanks. If you can fill in 3 of these blanks, you can use this equation to find the 4th blank. The M1 V1 equals M2 V2. I wrote the units over here on the side to show you that when I plug it into the calculation, when I plug it all in, that my value that I'm looking for here, my unknown, is going to be milliliters. You don't have to convert to liters on these equations. They just need to be the same units on either side. The answer would be 125 milliliters. You can never use this for stoichiometry. You can only use this for dilutions. Don't don't desperately look at the formula chart and start trying to plug in numbers if you're trying to set up a mole ratio. The mole ratio won't work in this equation. I like this picture because it shows in pictures how you would actually prepare your own solutions just by taking a solid in step A and then just adding water so that you will actually have your solution. As you calculated out the masses in step A, all you're doing is adding the appropriate amount of water. And notice that on these volumetric flasks, there is only one line. They put all their energy into one line, so this line is super accurate. They did skip one step at the beginning where you would actually have to add just a little bit of water down at the bottom so that when you add the solid or the solute, it has something to dissolve into, and it's not such, and it will actually dissolve a lot faster that way. Preparing your own solution and the materials involved in it are routinely tested on the AP test. We're gonna this video that I'm about to show is mostly for teachers, but it's great for students to watch. Cue the video.
The unique design of a volumetric flask with its wide body and narrow neck allows for extremely high accuracy when preparing solutions. Volumetric flasks come in standard sizes, with 100, 250, 500, and 1000 milliliter being the most common, and the typical accuracy tolerances are plus or minus 0.16 milliliter for a 100 milliliter flask, up to plus or minus 0.60 milliliters for a 1000 milliliter flask. Let's say you want to prepare a 0.100 molar solution of a pure reagent chemical. Using an analytical balance and a 1000 milliliter volumetric flask, you could in principle achieve a molarity that is accurate to 4 decimal places with a 0.06% overall error. The neck of a volumetric flask is marked with one line, which is typically referred to as the mark, as in fill the flask to the mark. Notice the flasks are labeled TC, or to contain, and a temperature is listed. Here are a few tips for taking full advantage of the potential accuracy of a volumetric flask. First, temperature matters. You need to be at room temperature, 20 degrees Celsius. If the solution absorbs or releases heat as the solute dissolves, allow the liquid to re-equilibrate at room temperature before filling to the mark. Second, don't waste good. Always use analytical transfer techniques. Transfer solids using a funnel. Rinse the weighing container, funnel, and sides of the flask with water or solvent. And dissolve or mix the solution with most, but not all of the water. Recall, volumes are not additive, and the density of a solution depends on its concentration. The final volume adjustment, that is, filling to the mark, should be made with as much well-mixed solution in the flask as possible. Use a pipette for best control in adding the final drops of liquid. Something many people forget, with the narrow neck, how do you thoroughly mix the solution to make sure that you have a uniform concentration? The technique I learned was to stopper the flask and invert it 25 times to ensure thorough mixing. And yes, I do count, silently to myself. When accuracy is important, volumetric flasks are a lifeline.